Okay, and I'm pretty sure with time we won't be able to do an example of both the scalar and vector value parameterized surface integral. So I'm going to show it to you for the vector just because I think those are a little bit harder. But, we can always go back and review this later and do another example. So we're going to compute oops. Sorry, I just dropped your book. So we're finding a surface integral for the vector field f equal to zi hat xj hat y plus z k hat. Through the parameterized surface r equal to u vi hat u minus vj hat 2u plus v k hat. Bounded by u equals 0, v equals 0, and u plus v equal 1. R equal. Okay, so first up, I'm going to identify my parameterized surface. So r equal uv, u minus v, 2u plus v. That tells me that I'm looking at the parameterization where x equals uv, y equals u minus v, and z equals 2u plus v. The reason I'm writing it in that format is because I know I'm going to have to substitute the parameterization into my vector field f, so it helps me to see what the x, y, and z are to plug them in real easy. And then I have bounds that were given to me for the parameterization. I'm told that u and v are both bigger than 0. And then also I'm looking at u plus v equal 1 bounding my region from the other side. So later on, we'll go ahead and set that up in a nice integral type bounds. But for now, we'll leave it there. And then our vector field f was given to us right here. Z, x, y plus z. And I told you the thing that's easy about integrating vector fields over surface integrals is that they're the only vector thing, so it's easier to identify them. And that's not true for parameterized surfaces. So if you're in doubt about which part is the vector field that goes inside your integral and which part is the vector field that sort of sets up your normal vector and region, the vector field in terms of x, y, and z is the one that goes inside the integral. The one that's in terms of u and v is a parameterization. So, and kind of the way that you can remember that, if it doesn't occur to you right away, is that one of the steps is going to be to take those x, y's, and z's and replace them with the u's and v's. So it'd be kind of silly to do that to one that doesn't have x, y, and z in it to start. So z was 2u plus v, x was uv, and y plus z is going to be u minus v plus 2u plus v. So that's going to be 2u plus v, uv, and 3u right there. Okay, and then we're going to have to take our partial derivatives to compute RU cross RV. And I'm going to go ahead and do that on the next slide because I don't want to take the partials and then have to copy them all over again. So our R was UV u minus v, 2u plus v. And so r sub u is going to be taking partial derivatives with respect to u. So here I'm going to get v, I'll get 1, I'll get 2. I'm not showing a lot of detail when I take my partial derivatives because I feel like we've been doing it for a while, but if that's still kind of like iffy for you, go ahead and pause and make sure those partial derivatives make sense. When I take the derivatives with respect to v, I'm going to get u in the first component. I'll get minus 1 in the second component. And I'll get 1 in the last component. And I wanted to compute this cross product, RU cross RV. It's been a while since we had to do cross products, but let's go ahead and bring them back. V1, 2, U minus 1, 1. So what I'm going to do is I'm going to, for I hat, ignore that component and look at cross multiplying those. So I'll get 1 times 1 is 1 minus 2 times negative 1. So minus 2 gives me plus 2. I'm going to remember to put a minus j hat and then ignore this component and cross multiply v times 1 minus 2 times u. So I'll get v minus 2u. And then plus k hat and ignore this row and I'll cross multiply and get v times minus 1 minus u. So that's minus v minus u. So that's going to be 3i hat, 2u minus vj hat. Remember that negative sign that flips the j hat component. And then minus v minus u k hat. And then my formula is going to involve f dotted with this component. So we're looking at this one right here. So I'll go ahead and compute that dot product. So my f was 2u plus v, uv 3u. And I'm dotting that with 3, 2u minus v minus u. So that's going to give me 3 times 2u plus v plus uv times 2u minus v plus 3u times minus v minus u, which is a lot, but I mean, it's just like powers of u and v. So 6u plus 3v plus 2u squared v minus uv squared minus 3uv minus 3u squared. And none of those components simplify, so that's what we've got. And we just have to set up our integral. So we're going to have a 2D integral with this thing inside. Integrating it with respect to u and v. And our bounds are going to come from here. Oh, actually, first I'll show you. In the steps, what I've done is I plugged in this part. I said this is a 2D integral, and we're just looking for those bounds. So we know that we're bounded by u equals 0, v equals 0. So let's go ahead and put that in. And then my u component goes first. So I need a bound for u in terms of v. So that's easy. I've got u less than or equal to 1 minus v. From that original that we had u plus v equal 1. So that turns into u equal 1 minus v. upper bound for u is u equal 1 minus v. And then my upper bound for v, I can get by setting these two things equal, and I see that v has to be 1. So here, I'll do it right here. So that's the first thing I did. And then I said, whenever I don't have an extra bound, I set the two things equal. So you had those bounds. So 0 equals 1 minus v. And I just solved that for v equals 1 for my region. And even though this looks very messy, it is a 2D integral with respect to integrating some quantity u, some quantity v. I have bounds that match those things. The bounds for u depend on v, and the bounds for v, which are outside, are constant. And everything inside is functions of u and v. So at this point, you could evaluate this 2D integral. And even though it has like 6 terms, they're all very simple power rule terms. So you could take this no problem.